maybe just so thank you first for all being there, or for connecting at least. This is I will say a few words about the workshop. So it is organized through the network GAMENET, which is a European network for game theory. And so this GAMENET supported in the past several events of this type. So there was a workshop 2 years ago in Budapest about stochastic games, and one last year in Tel Aviv about dynamics and information. And one of the specificities of this type of event is to feature more tutorials-based presentation rather than a regular research presentation, so that it caters for also for non-specialists, and it allows to make emerge new collaborations. And so so this time Xavier Venel and I, with also with the help of Galit Ashkenazi, Matthias Stodigel, Miklos Spinter, and Elon Solan, we organized it to be in Paris, but of course, because of the pandemics, at the end it's online. And the general topic is so games, approachability, and learning. There will be the first tutorial will be about a general introduction about approachability theory and its main application in learning. Second one will be about approachability in differential game, and the third one about generative adversarial networks, again, so tomorrow. And so our first speaker is Vianney Perchet, who is a professor at CREST NSA, and an expert at the interplay between game theory, learning, and reinforcement learning. And so thank you very much, Vianney, for accepting our invitation, and you have all our attention. Thank you.
Thanks, Bruno, for the introduction. It's a pleasure to be here in my home, and well, obviously.
Vianney?
Yes.
You need to share again.
Yes, I know. I am trying to do it while I was speaking, so it's. No, it should be working in like 1 second. It is working, and so it's a pleasure to be here with you guys, and here it goes. And yeah, so as we discussed before before starting this, before Bruno gave this few words, you might have noticed that I don't have slides, because I'm fed up with all those online conferences where it's I find them very hard to follow. So I decided to not make any slides, and instead I bought a tablet, and it will be I will be unwritten presentation, as if I was on a blackboard, but obviously not at a blackboard. So no slides, but unwritten presentation. So, but as you can see, my handwriting is not that good. So if there are any questions that you have, something is not clear, or if you have any question, of course, since it's a tutorial session, as Bruno said, feel free to interrupt and to ask questions. So without further ado, let's start this tutorial. So indeed, I will give a 2-hour presentation on the interplay between approachability and online optimization. And as you will see, my outline of this talk is going to be in a 5th part. I'm starting to do like Sylvain's presentation, lots of different parts. I hope I will be able to cover all of them. So the first one is just going to be a very simple motivation. So I'm just going to give you, ideas why I'm interested into approachability, not just take it as a tool and as given. Then we will actually show a small tutorial on approachability before getting this motivation. So that's the second part. The third part is I'm going to speak, go back actually here in the motivation. I will mention it's motivated by regret minimization. So the third part will be back to regret. And then the fourth and fifth pass is going to be more about practical problems and open problems. So the first one is going to be about bandits, and approachability. Let's call it like this, bandit and approachability. That could be the fourth part. And the fifth part is going to be about open problem. So I have many open problems, which is a good thing, because it means that if there's some students, or if you have students that are interested into this kind of stuff, I have material for them for many years, I guess. So feel free during this when we're going to reach this part about open problems, feel free to interrupt and discuss and start a discussion if you have other open problems, other questions, and everything. So maybe we'll have some. We could have an open problem, an open discussion, open problem session. Okay, but first thing first, let's look at my motivation. So the main motivation. So I'm not really going to speak about a game today because well, I don't have time. We only have two hours, so I'm not going to describe how approachability is actually used in game, for two reasons actually, because it needs lots of background, and I guess that if you're interested in how approachability is used in game, you already know how it is used. So I try to have a tutorial where I'm trying to give you a new idea, new insights, instead of just stating things you already know. So the motivation is what? Optimization. That's what I want to do, optimization. So optimization is, what do I mean by this? Let's say you have a function f. So we have a function f. We have this function f that goes from some subset x of Rd into R. And what I want to do is I just want to minimize this function. So I want to minimize over x, f of x. So that's a very simple problem. This is the optimization problem. You want to minimize a function. So sometimes you have closed form solution. So if you take, for instance, the easiest case is if you have let's say a polynomial of degree 2 or a polynomial of degree 3, you have like explicit closed form solution. But in many cases, you don't have closed form solution. If you take any polynomial of degree higher than 3 or 4, I don't remember precisely, let's say the degree is at least 5, so we are sure that it's not solvable by closed form, then there is no clear solution of this problem. Okay? Yes, is there a question? Or? Yes? No? Okay. Anyway, so sometimes there's no clear solution about this problem. So what you need to find an algorithm that minimizes this function, or that find a solution of this problem, or an approximate solution. So how such an algorithm is working, by definition, is it's something very simple. At first stage, you just try, say, well, maybe the minimum solution is going to be x1 in this constraint set x. And then you will get some feedback. So here I'm using this because I will play a lot with the type of feedback later on. So then you get some feedback. The feedback you can get is either what you say is zero further. So you just get to learn to compute f x1, or maybe you get the first order. So you're able to compute the gradient of your function, gradient of f of x1, or maybe the second order, you can compute the Hessian, and so on and so forth. And based on what is available to you, so maybe just the functions evaluation, if you're running simulation, for instance, of the gradients, if the gradient has a closed form and you can compute it by simulation or whatever, or if you have a function which is simple to do, you can compute maybe the Hessian and everything. You will need to, based on those feedback, you will update, you will try a new point, and you will try x2. And then you'll make some computation. Maybe you will get as feedback f of x2, or maybe the gradient, and so on and so forth. And based on this, you will query f x3, and so on and so forth. And the question is, if I'm giving you a budget of T iteration, the optimization problem is what is the error you're going to make, the optimization error. What you want to do is you want to control the optimization error, which is simply after T iteration, f of xt minus f of x star, where x star is the minimum of your problem, assuming there is a unique minimum and everything. And you want this to be smaller than something with high probability in expectation, or if you're in deterministic, just you want something this to be small or whatever. Or alternatively, I'm not going to look at this problem, but you can also require that the solution you output xt is close enough to the true solution, assuming there is a unique solution, same thing. Okay, so that's the optimization problem. You have a function f you want to minimize, and you have t iteration. And the question is, after t iteration, depending on your feedback, so the algorithm will depend on your feedback that you get, what kind of guarantee can you make on your error, optimization error? So that's just optimization. Okay, so that's what I'm interested into. So here, for this tutorial, I'm not going to look at this problem, optimization problem, because there is like hundreds of books on optimization. I'm going to look at different variants of this problem that we call online. That's the key ideas, is that I'm going to look at the online variant. So the problem which is called, so that's the online variant, online optimization. And usually here, we assume, for some obvious reason, that we're going to look at convex problem or linear problem. Maybe this one is too big. Up. Convex or linear. But that's irrelevant for the motivation, convex or linear optimization. So what is the main idea behind, or the main problem of online optimization? The thing is, we're going to assume that at each iteration, f change. So f changes at each iteration. So instead of being still being the same, it's going to be first, it's going to be f1, then it's going to be f2, and so on and so forth. Until the end, it's going to be ft. So what is the optimization problem that we want to solve? At first, we wanted to solve the minimum of f of x. But here, f is changing over time. So instead of looking at the minimum of f, which makes no sense, the objective is going to be, we're going to minimize, sorry, not f, but the average function f. So we want to find x that minimize this thing here. So that's the main problem. And obviously, we don't know in advance the function f, because we are doing optimization. That might be no closed form. So we're going to have an algorithm that queries sequentially, that makes sequential queries, x1 and x2 and x3, based on the function that he gets. And this is the problem, the objective, the criterion we want to minimize, this thing here. We want to minimize the over x, the average function. And what we want to do is, as before, I want to control my optimization error. But here, the optimization error has a different form. What form does it have? So that's the optimization error. It has a different form, and so it has a different name. And the name is called the regret. And what is this error? It's the difference between the average loss and this loss. Okay, so the regret is the difference, let's call it RT, the difference between, yes? Okay, so it's difference between...
La petite, elle est en haut. C'était son anniversaire.
Yeah, so Sylvain, I guess it's not a question. So you want to control the optimization error, so the difference between the average loss and the minimal loss of your objective. So that's the optimization error that we rename as regret. And I'm missing the sum here. Okay. Again, if you have questions, feel free to interrupt and to ask them. So that's the main question. So what we want to do is we want to build an algorithm such that this regret is as small as possible. Okay, so maybe here I could just mention two things about how those function f are generated somehow. There is two main cases. Let's do it. Okay, so we have two main cases about those function f. One of them is to assume that ft of x is actually a function f0 of x plus some noise. And this noise I'm going to write at theta 0 of, sorry, that's not a 0, that's a t of x. And in that case, you can if you are used to optimization, you can see that this problem is basically the regret is going to be, if I write the regret is going to be the difference. And here I'm going to assume that the noise have zero expectation for every x. Okay, I'm going to assume. So if I'm looking at the expected regret is nothing less than f0 of it's smaller actually x bar. That's the average query minus f0 of x star. Okay, so I did it on a wrong direction here. So here, if I'm taking this first case where the function ft are a base function f0 of x plus a perturbation of this function, stochastic, so that its expectation is 0, and maybe the expectation of this gradient is also 0. Here, it's nothing less, nothing more than what we call stochastic optimization. So online optimization is a generalization of stochastic optimization. Okay, if I'm putting more assumption on my model here, if I'm assuming that ft is a base function plus some noise, I'm ending up in this stochastic optimization problem. Okay, so that's the first thing, and the main cases. And the second main case is on the other way around, what we call adversarial case. That's why it's related to game theory. Let's call it adversarial framework. That's the total opposite. You know, in the stochastic case, we have a lot of structure. We assume that ft is always the same function plus some noise. And in the adversarial setting, we're going to assume the opposite. We're going to assume that ft can be anything. Ft can be anything, can be any function. Any function. And it's even worse. It can even depend. It can even depend on, on the past. So what is the past? Well, the past is x1, maybe f1, x2, f2, up to xt minus 1 and ft minus 1. Okay, so here we end up somehow as we have a game between the optimizer that want to minimize, control, his objective is to control the regret, and the other one is nature that outputs ft. But the sequence ft. Here, the difficulty of this when I speak about game, the difficulty is that I do not put any assumption on nature. I don't assuming that, for instance, nature is trying to maximize the regret of the optimizer. because we will end up in some zero-sum game, and actually it's not always the case. Sometimes nature is not that malevolent. Sometimes nature is not picking loss function as the worst one. Sometimes it's not that bad, and so I'm not going to make any assumption on nature. She can choose any loss function ft. So what I want to do is we want to design an algorithm, an optimization algorithm that is good. So I'm just going to say good, like it's good, it's good, without saying anything what good means. But I mean it's a unwavy that is good. Okay, let's call it good. So you take a criterion, the one you want to, the one you like. Okay, that define the goodness. So we want to find an algorithm which is good against any sequence of function. Not just the worst one, as in the zero-sum game. Not just the one that will maximize some nature utility, because we don't know the utility of nature. So we want to have a very robust algorithm, a very robust optimization algorithm, which is good. Again, good can mean many things. And here, basically, good meaning that the optimization error, called the regret, so our regret is going to be small. Okay, and this has to be true against any sequence ft. That will be our objectives. And a very nice way to do that is to use the approachability theory of Blackwell. And that's why, of course, the connection between regret, online optimization, and regret. So specific case that's going to be interesting for us. Here, just for the sake of the presentation, because we don't have time, we don't have an infinite amount of time. So I'm going to look at some specific case. I'm going to make some assumption, specific cases. I'm going to look at linear function, linear mapping, linear loss function. Okay, so I'm going to assume that ft of x is simply a linear function, at transpose x. Okay, so basically what nature is doing is picking at each stage some vector at. And I'm going to assume that that's the first point. I'm going to assume that x is a polytope. Again, this is just for simplicity. I don't need this. Okay, a polytope meaning that it's just a convex hull of finite number of points. Okay, and since I assume that x is a polytope, at very small cost, actually it's not true, but it's, again, if you're interested about this problem, going from the simplex to something different, we can discuss it later on. I'm going to assume that it's not only just a polytope, but that x actually is going to be the simplex. Okay, so I'm in RD. So basically, it's going to be the convex hull of the base vector, A1, A2, A2, AD. Okay, those guys here are the basis vector, canonical basis vector. Okay, so it's just 1, 0, 0, 0, 0, 0. Okay, so X is the polytope. And maybe a last thing, I'm going to also assume that AT must belong to some set A, which is, let's say it's compact. That's a subset of RD. So that's the three main assumptions I'm going to make. All of them are needed, actually. We can go way beyond this, but it's not really the purpose right now. Okay, we don't have time to look at all of those extensions. But it's possible to go beyond the linear case, beyond the polytope case, beyond the finite dimension case, beyond the compactness case. It's possible. Okay. So let's look at that's the main setting. Okay. So now I want to define. I want to find an algorithm, again, an optimization algorithm that is good against any sequence ft, so against any sequence of AT. And being good, I remind you that I want to minimize the regret. Okay, so here what I'm going to do is we can move from the regret up to vectorial formulation. And this is what I'm going to do right now. I'm going to show you how we can rewrite the regret vectorial formulation for regret minimization. Of course, this is going to be true for this very specific case. I'm going to use the structure I've just defined: linear function, polytopes, and compactness of A. But again, it can be generalized. Okay. So remember that RT, the regret, the optimization error, was defined as the cumulative loss of an algorithm. So it's AT transpose, because here I'm going to assume that my that X is going to be this convex L. I'm going to make well, okay, let's take it like this. Actually, it's okay. So RT is the difference between the cumulative loss of my algorithm minus the minimum over all of the point X in X of that's the optimization, the optimal minimization of my average loss, AT transpose X. So that's the regret. And you remember that being good means that this has to be smaller than something. So here, I'm going to do the first trick. As you remember, we made the assumption that f is linear. So this function here, obviously, is linear. That's not very difficult. It's a function which is linear and which is minimized over a compact set. So the minimum is going to be attained at one of the vertex, on one of the vertices of X. And those vertices as either E1, E2, or ED. So I have D vertices. So here, basically, I can just remove this thing here. Instead of just looking at X, I can just look at the vertex, the vertices of X. So I have D vertices, E1 up to ED. So here I can minimize over I. So this notation here is, I'm going to use it later on. This is the set of integer between 1 and D. In France, we have a specific notation for this guy, that it's only French. So maybe I should, so in French, we call it like this. We have this notation for people that are not French. Just we write this set, the set of integrals is written like this. Okay, so just an apart. And so AT transpose E of I. So this is a way to rewrite regret. But here, still not vectorial. So I'm going to rewrite it in a vectorial setting, saying instead of looking at the minimum over I, I'm just going to say that for each I, this thing has to be smaller than 0, which is trivial. So what I can say is I can just rewrite everything as a vector. And what I want to do is I want to ask that the sum from t equals 1 up to t. And here, I'm just going to write it as a vector. I'm going to assume that AT transpose xt minus the loss of the vector, the vertex EI of my simplex. I want this to be smaller than 0, asymptotically smaller than something. This should be O of 1, right? Something that goes to 0. But the question is how far it goes to 0. And this has to be true for every I. And then here, I have a vector formulation of the regret. That's equivalent. And this is exactly what I'm going to do. So here, instead of having something like this, I'm going to assume that this is an average vector. So since it's a vector, I'm going to write it as V of xt and AT. And I want that this vector has all of these components that was component-wise, of course, component-wise. So here, what I want is I want this average vector to be component-wise smaller than 0 asymptotically. So I want that this vector converges to the negative orthant of RD. Or maybe instead of belongs, I want to maybe do converge to as t goes to infinity. So here I have my approachability. I have everything I need for an approach to motivate the approachability case. So what do we have? We have a finite vector game between two players. So we have P1, which is the optimizer, which was the optimizer, and P2, nature. So what is the strategy space? So P1, it chooses xt in the simplex. So here in this simplex, the simplex, I assume that simplex is D, but I don't really need this simplex to be of dimension D. I can just assume that xe is in simplex of dimension M. Okay, so that's again that's the convex hull of M point. Okay, that's the probability over the set of probability over a mixed strategy over M point. Okay, that's the probability over the set M. Okay, so player one choose a set at random. So either it choose a mixed action, okay, or a pure action. You can choose. We can decide to make it IT in M. It's the same thing, you know. Basically, either you use in pure action, so that will be, you know, if you have a game in mixed action here, or here in pure action. And actually, for our purpose, for regressionization and approachability, mixed and pure action is basically the same thing. So P1 does that. P2, that's nature, is going to choose AT and in subset A. In some convex set A. Here, if I want to do the same thing, okay, let's keep it this way. Assuming that this is a convex compact. Convex because otherwise I can just randomize. So I can, it's without loss of generality, and compact for simplicity. Okay, so P1 choose XT, P2 choose AT, and the outcome, I'm going to use the word outcome instead of reward or loss. The outcome is a vector. So if player one choose IT and player two choose AT, the vector outcome is V. It's a function, V of IT AT. So that's a vector in RD. And yeah, maybe here I could say actually it's going to choose AT instead of I'm going to pick GT in I'm going to assume that we have a finite set for simplicity. So player one choose pure action in M, and player two choose a pure action in N. So that's exactly the same setting, it's just for simplicity. Okay, so because so that I have a set which is defined, which is well defined, because it's easier to define vector functions on a finite set than on a not finite set. Okay, so that's the game. Okay, so action set of player one is 1M. Action set of player two is 1N. And if player one choose I and player two choose J, so that's stage T. Okay, it's going to be repeated, so that's stage T. The outcome is V of ITG. Okay, and what is the objective? The objective is, as we have seen here, is the convergence of the average vector to some set. Okay, so that's the outcome is like the reward function in a standard game, and the objective is what is defined by a set C. And I'm going to assume for this talk that the set I'm going to consider is convex. So the objective is that given the convex compact, I don't really need compactness, but that's again it's always to simplify thing. A convex compact set C, so that's in RD. what I want to do is I want to be sure that the average vector, so if I need a sum, converge to C. And here, what does this mean? Well, it just means that the distance from the average vector to C goes to 0, with T goes to infinity. Okay, I don't need the average vector to converge to some specific points. I just need that the average vector converge to the target set C. And this is the main setting for approachability. Finite action space. Again, it could be convex and compact. That's very simple. A vectorial outcome. If player 1 choose I and player 2 choose J, the outcome is V of ij. And the objective are described by convex compact set C. And the objective of player 1 is that the average vector converges to C. And that's what has been introduced considered by Blackwell and what is called approachability. So that's what. Then we're going to
Hello.
Yes.
I have the one question. Like,
sure.
Can you tell separately what is the objective of two players? Like, is it like first one is trying to approach a negative orthant, and second one is pushing out? Is it like that?
So yeah. So that's the objective of player 1.
Okay.
The objective of player 1 is that the average vector converge to some target set. So in the previous example, you were right. The objective of player 1 was that the average vector here converges to the negative orthants here. Okay. So in this case, this was the convex target C. So that's the objective of player 1. And here we don't really need to specify the objectives of player 2, nature, because I want to define a strategy which is good against any strategy of player 2. But in this very specific case where I have convex and compacity, actually convexity is enough. The objective for player 1 will be, so player 1 wants to minimize this distance, and player 2 would like to maximize this distance. Okay, so one player tries to push the average vector towards C. That's player 1. So he wants to put the regret towards C. And the other player, we can assume that the other player is trying to push the regret farther away from C as possible. But this, we don't really need it, actually. I don't need to specify an objective of the second player. Okay?
Okay,
but that's the idea. Again, this is the idea. The idea is that player 1 is trying to push the average vector towards some target set C, and the other player, nature, tries to prevent him from doing this. Okay, so basically, so now now I've written this. Actually, it's something I was going to say later on. Here, basically, what we can see is we sort of having a min-max zero-sum game, sort of, because player 1 tries to minimize this function here, the distance, while player 2, on the other hand, tries to maximize this function. So it's kind of a zero-sum game, where the loss would be the distance, but it's not really a zero-sum repeated game, because this loss here, the distance to a compact set, is not an average loss, it's not a cumulative loss, it's more like a global loss. So it will be a zero-sum game where the loss function is a zero-sum game defined in terms of strategies and not in terms of instantaneous payoffs. It's not a repeated zero-sum game. It's a zero-sum game over the space of strategy. And it's a bit more complicated than this because it's not really a zero-sum game, because here what I want is player 1 wants to asymptotically that his payoff converges to 0, while the other one wants asymptotically that his payoff does not converge to 0. So it's sort of a zero-sum game, except that here it's a long run. Okay, it's a zero-sum game in the long run. Player 1 in the long run wants that the loss converges to 0, while player 2 wants in the long run that this loss is not equal to 0. Is that clearer or?
Yeah, I have a question.
Yes.
You said before that making zero-sum assumptions is too strong and you can do less than that, or you're interested to do less than that.
Mhm.
Then why do you restrict here to a zero-sum instead of restricting, saying that player 2 wants to get to another compact set, say, and then in particular, in particular, one could take this set as the complementary of the other as a special case.
So yeah, it's you're right. Here in this case, player 1 basically the objective is that player 1 wants that the average vector, let's call it VT, converge to C. And here I'm just assuming that player 2 is going to try, but that's a way of saying it. I just say that I don't care what player 2 is doing. Player 2 can do anything, okay? But here, if I want to be sure that the average vector converges to C, I can assume that player 2 wants that the average player converges to the complement. You're right. But I don't need to make those assumptions. I want to have a strategy for player 1 which is good against anything that player 2 could do. So player 2 could try to make this average vector converge to the complement of C, so that we have like it's exactly having a min-max situation. We could ask for player 2 to maybe player 2 wants that this average vector converge some specific set, another set. So here I could have like a set C1 for player 1 and a set C2 for player 2, and maybe a player 2 wants actually to converge to C2. But all of those things actually are irrelevant in the convex case for the following reason that we're going to see later on. But here, maybe let me be a bit more clear on what I assume that player 1 was not, what I meant about min-max, the difference between min-max problems and the fact that I want something stronger than just being robust to min-max, to this min-max case. So here, let's take as an example for regret minimization. I'm going to assume that so player 1 has 2 actions and player 2 has 2 actions, okay? And I'm just going to look at this very simple zero-sum game, okay? So let's say that player 1 plays has 2 actions, okay, 1 and 2, and player 2 has 2 actions, so 1 and 2, and the reward of that's the reward of player 1, or the loss of player 1. Let's create a loss. I'm using the loss term from the beginning. So the loss of player 1 is either 0 or -1, -1 or 1. Okay, so here I have this. So that's the basic problem that I defined before, right? Or where player 2 picks a column and player 1 picks a row, and the loss function of player 1 is either 1 or -1. So here, what I said is if nature was trying to maximize P1 loss, we will end up in zero-sum game. So okay, if we were at each stage, if we assume that nature was trying to maximize the loss of player 1, we end up in a zero-sum game because player 1 is trying to minimize its loss, player 2 is trying to maximize it. And so the optimal strategy of here, the optimal strategy in this repeated zero-sum game, oops, this is the optimal strategy, will be at each iteration play xt, which is 1/2, 1/2, right? You play at random the first and the second row, and you get this gives an average reward, an average loss of 0. Okay, so here, if I was looking only, if I made the assumption that nature is trying to, in the regret case, nature is trying to hurt, is trying to maximize the loss of player 1, I will end up in a zero-sum game, and I will solve this zero-sum game at each iteration. And player one will play at each iteration. He will play an optimal strategy. But here, what I'm saying is, I want to build stronger, more robust strategies that are good against any sequence of choice of nature. In particular, here, I can assume that, so we want to be good. Remember, I want to be good against any sequence. Good against any sequence. So in particular, I want to be good against the sequence that says that player two, nature, picks the first column at each iteration. So I want an algorithm which is good against the sequence of choices of nature, which is always the first column. And in that case, if nature always picks the first column, we can see that the optimal strategy is no longer to play 1/2, but is to play bottom. So if you play 1/2, this will give an average reward of 0, an average loss, sorry, same thing, 0. But if for this sequence, this very specific sequence here, 1, 1, 1, 1, 1, it's possible to get by playing 0 and 1, it's possible to get an average loss of -1. Okay, so even if you have a structure as a zero-sum game, which is repeated, so on and so forth, I'm not going to make the assumption of on nature behavior. I'm not going to assume that point-wise nature is going to try to maximize the loss of player one. Because if I'm doing this, then the solution is simple. You just solve the zero-sum game and you play repeatedly the optimal action. Here, basically, what I want to do is I want to learn whether nature is actually trying to maximize my loss, or maybe she's not trying to maximize my loss. Maybe she is in a state where the action she chose is always the first column. And in that case, I need to learn this and play bottom as fast as possible. But here I must be careful, because maybe actually she's going to play 1 at the beginning, and then she's going to play 2, the second column. So I will have to switch at some point to stop playing the second row and play the first row. That's what I meant by I want to be stronger, I want to be more robust than just doing min-max. Okay? But here, that's why, I mean, and if you look about in this situation here, when I look at then at the distance, you can see that basically here it will say that I have an average loss of 0, and here if I play bottom, I will have an average loss of -1. So here my regret. So if I'm playing 1/2 at each iteration, the average regret will be 1. Okay, it's 0 -1, so 1, and this does not go to 0. So I can assume that nature is trying to, I cannot assume that nature is trying to minimize the loss of each stage, but I can assume maybe that nature is trying to minimize the regret, which is fundamentally different. So nature is trying to maximize the regret and not maximize the loss. I want to have, because if I assume that nature is trying to maximize the regrets, I will have a strategy which is good against any sequence, any possible sequence of nature. If I'm assuming that nature is only trying to maximize the loss per stage, I just need to find a sequence which is optimal, which is stepwise optimal, which is very different, as you can see here. Being stepwise optimal is 0, min-max optimal means that you play 1/2 at each iteration. That's trivial. But being optimal against any sequence in the long run, finding an algorithm which is good is way more difficult, because you need to be adaptive to the choice of nature. So that's the main difference. So here we can, yes.
Sorry. So in the same topic, is it fundamentally different to minimize regret and to minimize the mean payoff, the mean reward, or is it the same?
Oh yeah, it's the same, because as you can see, if I go back to the regret, the definition of regret, you can see, so that's the definition of regret here. This quantity, this quantity is more or less independent from your, at the end, this is independent from your algorithm, okay? So minimizing the average loss or minimizing the regret is the same thing. It's just looking at the optimization error is just a way to normalize things. But this is standard in actually in optimization. When you're looking at this quantity here, for instance, an optimization, and if you look at the optimization error, this is minimizing the optimization error. So the difference between f of xt and the minimum of f is the same thing of minimizing f of x t. Okay. The only thing is that looking at the regret or at the optimization error instead of looking at the at this very quantity here is a way to normalize things, and it tells you that your algorithm is good or not. Because if I'm telling you that your optimization error or your regret, so if you have like, if I'm telling something like okay, or even for an optimization function, okay, let's say that you want to optimize, so you optimize f. You want to optimize f, and you have an algorithm, and you say that f, you tell me that f, or I'm telling you, at the end, I got f of ft, which is basically, let's say 1. I was able to find a point such that f of xt is 1. And then I'm just giving you this as a solution. You have no idea whether my solution is a good solution or a bad solution, okay? Because maybe this one here is optimal. Maybe f of x star is actually equal to 1. So here I gave you the optimal solution. Or maybe f of x star is minus 100 for some reason, and actually the point I gave you is very bad. So the value of f of xt, or the value intrinsic value of the loss of the average loss in the unalike case makes no sense. Okay, what is important is how far you are from the optimal. So that's why we look at the regret or at the optimization error, is just to have a way of saying, well, you were this far away from the optimal, so your algorithm was good or your algorithm was not that good. Your strategy was a good strategy, or your strategy was not a good strategy. Okay, but actually at the end, you are totally right. It's the exact same objective, except that one of them is somehow you can interpret what he's saying, saying, well, you are epsilon optimal, and the other one, you cannot interpret it. So, by the way, I saw that there was some question in the chat, and I have no way of looking both at the chat and everything. So,
Yeah.
so yeah. It was not a question. So anyway,
I don't think it was a question.
Yeah, but is that yeah? I saw there was just a.
But if it's the case, we will tell you.
Yeah, thanks. Okay, where was I? I was over here. Okay, so let's move to we know how the case of approachability. That's the second part. That's the tutorial. I call it tutorial. The short tutorial. Let's put it short. On approachability. So let me just say right now that there are many people working on related topics, including in the audience. But there is I've written a survey which is like part of my introduction of my thesis on those problems, and you can find them on what was the name of this survey? Approachability, regret, and calibration, something like this. Approachability, regret, and calibration. Actually, I have it open right here because in case I forgot something. Approachability, regret, and calibration, implication and equivalence. Where you have way more details than what I'm just going to say right now, but so it's in GDG, Journal of Dynamics and Game. I guess it was in 2015, 14 actually. So you can find lots of materials in it, especially all the reference that you might need for all the, I say that what I'm going to say here, it can be generalized in many different ways. So look at the reference, and you have many references where you can find what you like. There's 100 references. So and I know that people in the audience are also working right now on approachability. So I mean, feel free to ask me or them about those questions. Okay. So let's go back to just a reminder on our problem. So we have a finite vector game. Player 1 choose either a mixed strategy or pure strategy, I. Player 2 choose GT, a pure strategy. The vector outcome is V of IT GT here. And the objective is that the average vector converge asymptotically to C. And Blackwell, so here it's due to, everything is due to Blackwell in this talk actually. And he defined a concept of convergence. And he says that a set, let's say a convex compact set C, including in RD, is approachable by player 1. That's the main definition. So by player 1, if player 1 has a strategy, so strategy is defined as usual, strategy call it sigma, such that for every epsilon, after some time, there is some time, if the number of iterations is big enough, then no matter the stage, the further stage, no matter the strategy of nature, the payoff will remain epsilon close to C. So the payoff, the average payoff, so here I'm going to change this notation, is epsilon close to C. Okay, and this of course will be incorrect if it's written like this. So I have to define what kind of convergence I'm going to look at, and for this talk I'm just going to look at expectation, okay, over the strategy. So this is the concept of convergence. It's not just convergence, it's convergence at a uniform rate. So a convex set is approachable if I have a strategy, if player 1 has a strategy, such that for every epsilon, after some time, T epsilon, the average payoff is for sure epsilon away, at most epsilon away from C. So that's the definition, a very strong definition of convergence, but it's the good one. Why is it the good one? Because it's the strongest possible one, and we have this main results. So we have the main results. The main results of Blackwell. And as I said before, this is more or less, this is an equivalent of well, how can we say this? I said the equivalent of a min-max theorem for vectorial, for vectors payoff, for vectors. Okay, so what is this main theorem saying? Saying the following. First point, C is approachable by player 1 if and only if for every mixed action of player 2. Okay, so can you hear me, or do you hear me? No?
Yes.
Oui.
And you can still see, okay. No, because I see on this screen, I said that, yeah, it was, my iPad was working in disconnected mode. Okay, so if for every mixed action of player 2, there exists a mixed action of player 1, such that the vector payoff is in C. Okay, so this is the equivalent of min-max theorem, because here you can see that this says that the max over y of the mean over x of the distance of v of xy up to c, this is equal to 0. So that's a max min, but this is not really the min max. This just says that the minimum over the strategy sigma of the maximum over the strategy tau of the distance of the average payoff at stage t up to c is smaller than epsilon. Okay, so that's why it's more or less an equivalent of min-max theorem for vector function, but it's not exactly a min-max theorem. Okay, because on the right hand side we have the max min, which is the distance from v to c, and on the left we don't have the min-max. We have only asymptotic results, but that's why it's more or less equivalent to a min-max theorem. And that's the title of Blackwell's article. Actually, it's like an equivalent of min-max theorem for a vector function or something like this. The second point is very interesting. It says that the concept of approachability, the convergence, type of convergence implied by approachability is the strongest one possible. It says the following: C is either approachable by player 1, or, so it's one or the other, excludable by player 2. What does that mean, being excludable? It means that player 2, I'm going to write it in green, player 2 can approach the set, I'm going to write it like this, the set of Z, such that the distance from Z to C is bigger than delta, for some delta. Voilà. I'm just going to write it like this. Okay, so that's the second part of Blackwell. So here, I just want to say that not being approachable is not equivalent of being excludable, because the order of quantifier is not the same. If a convex set is not approachable, it means that no matter the strategy of player 1, no matter sigma, there exists some epsilon such that for every t epsilon there exists blah blah blah. Okay, so the convex set is not approachable if for any strategy of sigma, player 2 the nature as a strategy such that the average payoff does not converge to C. Being excludable means that player 2 has a strategy such that no matter the strategy of player 1, then we don't have convergence. So it's not the same thing. Okay, it's like the min-max and max-min. It depends on which plays first. So here, this statement, the second statement, actually says, it's also a part of the equivalent theorem. It says that either player 1 can approach C, or player 2 can not only prevent player 1 from approaching C, but he can approach a set which is far away from C. And far being delta away. And here I'm going to write it like this, because we have a break now at some point. And the following strategy. Oops, I have my iPad that again that you can see it's written that something is not working. But okay, the following strategy approaches C, of course, if it's approachable. So let's do the following. At step t+1, what is the strategy? It's quite simple. Compute the average vector, Vt, which is, well, the average outcome up to now. Okay. And then, so that's the first thing. Second thing is solve the zero-sum game. Which one? The one defined by this. So player 1 wants to minimize over is x. Player 2 wants to minimize over the mixed section of the inner product between v of xy minus the projection of VT bar, projection over C, and VT bar minus the projection over C of VT bar. So solve this, and then choose IT plus 1 according to XT plus 1. XT. So that's the minimum here is going to be XT plus 1 star. Okay, so you find the solution and you play this thing. And this strategy approaches here in the sense that the expectation of the distance from the average vector up to C decrease as we want, and it decrease as, that was not very, 2 times square root of V over T. And this, what I do have here is, I'm going to write it like this, V2 infinity square. And this thing is the maximum infinity of the L2 norm. Okay, so that's the maximum over Ij of the L2 norm of Ij. Okay, so this gives me a rate, which is, this gives me the approachability requirement that the average vector covers to C at the speed of with a speed which is independent of the strategy tau used by nature. And yeah, so maybe we should do the break right now. Just a few words, just saying that this is we're going to do maybe the proof because it's quite simple later on, just over this result. And the proof is purely geometric, and this is quite important actually because everything I'm going to say after is geometrical question. We're going to ask ourselves a lot of questions about the geometry of the space, and that's it. Okay.
Okay. Thank you very much, Vianney. So we will restart in 15 minutes, so 11:20. Thank you.
Okay. Shall we start again, or?
Yes.
Well, actually, it's good. Okay, so it's not sharing my screen. Okay, in 3, 2, 1, and good. Okay, so let's start again. So we had this this main theorem of Blackwell, and because it's everything I say now is going to be related to the geometry of the space, of the ambient space, we're going to look at the proof because it's so simple that it needs to be, it has to be done. Okay, so let's look at the proof of this. And this is going to be, no, actually I was going to say it's the only proof I'm going to do, but actually it's not true. The first thing about this proof that we're gonna show is that this zero-sum game here, that is defined here. Oops, well, it's not working. This zero-sum game here has a value which is always 0. So why is it the case? Let's make a picture instead of so that's the first point. First point, the zero-sum game introduced. The zero-sum game has a value which is smaller than 0. Not necessarily 0, actually, smaller than 0. So I'm going to keep it like this. So why is it true? Well, let's consider. So I'm going to do a picture. That's a proof by hand waving. So here I have my set C. I'm going to look at VT. VT is going to be over here. Say the projection of VT over this set is going to be more or less here. So that's the projection over C of VT bar. And this means that by definition, oh, this is so ugly. Is it recording or? Yes, it is. That's too bad. It means that here I have those two vectors are perpendicular. Okay, and remember that we assume, Blackwell assumes that for every y there exists x such that v of x y is in C. So as you can see, so it means that for every y there exists x such that v of x y is in C. So for every y there exists x such that the vector is over here in this point. So that's v of xy. And you can see the zero-sum game is the inner product between v minus the projection. So this is this vector here. That's v minus that's vt bar minus the projection of vt bar, and vt bar minus no, this is this one, the one on the left, and v of xy minus the projection is this vector here. So that's v minus p of vt bar. So as you can see in this picture, because we have a convex set, for every y there is h that v of xy is smaller than 0. This means that the max mean of the zero-sum game is smaller than 0. And since we have a game which is linear, because v is linear in x and y, and when I take the projection, it's still linear. So I have a zero-sum game. I have a game which is a zero-sum game where the loss function is convex concave. So in this case, concave convex. So the max mean is equal to the min max, and so it says that the value is smaller than 0. Okay, so here it means that when I start the zero-sum game, I know that this thing here is smaller than 0. So xt plus v of xt plus 1y, no matter what y is, minus the projection times vt bar minus p bar is smaller than 0. So that's the first point, and it's actually crucial. Second point, now that we have understood this geometry, that's where the geometry kicks in, we just need to expand everything. So the proof is only like 2 lines, and it goes as follows. So I want to look at the distance from vt plus 1, the average at stage t plus 1, minus the projection at t plus 1. I'm going to take a square. I'm going to show that this decreases as 1 over t. And how to do that? Well, this is quite simple. First thing is, by definition of the projection, this is smaller than vt plus 1 bar minus the projection of the stage of the step before. Sometimes it's equal, sometimes it's strictly smaller. And now I'm going to use the fact that for averages, this is equal to t over t plus 1 vt bar plus 1 over t plus 1, the vector at this next step, vt plus 1. This guy here is going to be, I'm going to make it in green. I like this light green. So this guy is v of xt plus 1, of it plus 1, gt plus 1. So minus the projection of vt bar square. And now I'm going to use the only things I need is I'm going to expand this this sum, and this is going to be smaller or equal. Actually, this is equal. I'm going to expand this square now. So it's t over t plus 1 square times vt bar minus the projection plus the inner product 2 times t over t plus 1 square, the inner product between vt bar minus the projection and vt plus 1 minus the projection, plus 1 over t plus 1 square times vt plus 1 minus the projection square. And now I'm going to take, take everything in expectation. So I'm going to put expectation here, 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 everywhere. And as you can see, I'm done now because, so here I have the expectation, which is also here. And the expectation of this thing here is the smaller than 0 because of the first point. Because here you can see this is, when I put the expectation, this is here, this thing here is exactly the reward of the zero-sum game. So that thing here is smaller than 0. So it's smaller than 0, so I can just remove it. And I end up with the following recursions. I have t plus 1 square, the expectation of vt plus 1 bar minus its projection is smaller than t square times the expectation of vt bar minus its projection. Plus, well, here I have the expectation of vt plus 1 minus pi square. This is smaller than 4 times the to infinity squared. And now this tells me that this implies, because this thing here obviously is the distance of vt bar up to c, and this guy is the distance of vt plus 1 to c square. If I'm doing these recursions, I know that the expectation of the distance of vt plus 1 bar up to c square is smaller than 4 times this guy here. Yes? Is there a question? Okay. And so that was Blackwell's result. And so it says that if this gives me, so here I have proved the third point. Okay, that the strategy is working. I have proved the first point. And for the second point, actually, if I go back to prove the second point, it's also a matter of geometry. So if I'm taking C, and if I assume so I know that if for every y there is x, so that v of xy is in C, I know that C is approachable. So now I'm going to look at the case where there exists y such that for every x, v of xy is not in C. So what happens if there exists y such that for every x, v of xy is not in C? Well, this just means that for some while, all of the v of xy are like this. So this guy here in a green, I'm going to make it green right now. This set is the set of all of the v of xy for x in the mixed action of player 1. And I know for every y there is such y, this one, so that for every x it's not in C. And the thing is, like the distance between those 2 points, I call it delta. And I know that, so if player 2 plays y, let's call it this y star here, play y star at each stage, each step, then VT bar will converge to this green set. So the distance of VT bar up to C is going to be bigger than delta. And that's it. That's the proof. So it's a very simple statement, as you can see, because the good thing is it tells you that you can approach a convex set C, so you can satisfy the objectives that are given to you, making, if you're an optimizer, making an average vector converge to C, if and only if you know in advance what nature is going to do. So if you know in advance what the mixed action of nature, if you know in advance this mixed action, you have a best response, you have a response such that your vector belongs to C. So if you know in advance what nature is going to do, you have a response such that the vector loss, the vector outcome is in C. Then you can also do it in the long run when you don't know in advance what nature is going to do. So that's the main results of Blackwell. So then it's very simple to prove existence of strategies. So here that's what we'll do right after. Maybe a few remarks. This proof can be generalized for a high probability bound to get high probability bound. Can be generalized to get in infinite dimension. Why is it possible? Basically, well, because when you see the rate of convergence, so that's a V, that's not a U. The rates of convergence here are basically independent of the dimension. The dimension does not appear anywhere apart from the fact that it might be hidden in the definition of V, but the dimension does not appear anywhere. So it can be generalized to infinite dimension. It can be generalized when some with activation function. When some coordinates are active at some stage, some others are not active. When the convex sets are not convex and are for not convex set C, and so on and so forth. So all of this kind of stuff here, there is work by let's call them Mertens, Sora, and Zamir. I'm going to put some name. You can look at the book. We have Mertens, Sora, and Zamir. Oops. He almost been a Samir. It's Zamir. You can see there's a lot of paper by Ehud Lehrer and Elon Solan. Oops. Sorry, Elon. You almost got a Sloan. Elon Solan. I have some paper. Also Manor, Shai Manor, that has a lot of paper on this kind of stuff. And Nahum Shimkin. And I want to mention also there is a recent work by, not so recent right now, but by, you can look at Abernethy, Jake Abernethy, and Peter Bartlett. It's quite interesting. So those guys are more machine learning, and many other. And student of those guys, and well, I was a student of Sora, so I'm including myself in the student of those guys. And yeah, I know I'm forgetting some people, but please don't be mad. Don't be mad. It's if there is an obvious person I have forgot, please just raise your hand right now and shout his name, so that we are everybody's happy. No one? Okay, great. So it means that I forgot nobody. So let's go back to the regret. So here we have everything we know about the results. So we have the approachability main Blackwell main results. So let's go back to regret. Back to regret. And you remember I call it this online optimization. Let's put also Gilles Stolz here. Maybe with a T, Stolz. Okay, so we have the Blackwell's results in our hand. What can we say with it? Is it useful or not really? Well, the first corollary that we can derive from this from Blackwell results is the following: there exists strategy. There exist strategies. Let's put the plural that minimize such that the average regret, expected average regret, converge to 0, and we can be more precise. We know that the average regret will be the expectation of I'm going to so remember that the regret was the sum from t equals 1 up to capital T of AT transpose xt minus 1 over t, the sum from t equals 1 up to t of AT transpose EI. So that was the regret. But I also have a minimum here. So what I'm going to do is I'm going to take the maximum here with a 0 here and put a square. So that's a way of writing the regret. So I know that this guy here is, because of Blackwell results, is smaller. So I don't really here. I'm going to introduce a notation because I'm going to get rid of all the constants. So this notation here means that there is some hidden constant, square root of d over 2. So here, this wiggle here, this means that I am hiding a constant. And here I want to emphasize something, like a constant is 2. D here is not a constant because D can be worth either 2 if you're in dimension 2, 3 if you're in dimension 3, 1000 if you're in dimension 1000. So D is not a constant. D is a parameter. D changes depending on your definition of D. On the other hand, 2 is always 2. And pi is always 3, 14, something. Okay, so those are constants. D here is not a constant. So this tells me that this is basically telling me that the regret, the expected regret, is smaller up to some constant to square root of t over. And the proof is 1 line. Proof is 1 line. Remember that RT being smaller than 0 was equivalent to 1 over T, well, actually was equivalent to VT. VT bar belongs to the negative octant, where VT basically was this was this guy here's difference was VT bar, the IF component of VT bar. Okay, so if I want to apply Blackwell theorem, I just need to prove the following. I just need to prove that for every y of player of nature, there exists x of player 1, such that v of xy belongs to R minus d. Okay, but remind that v of xy, this was equal to, well, maybe here I'm going to put an A to simplify our notation. And here, instead of having this convex set here, I'm going to use convex set A, the same thing, the exact same proof. So V of XA is A transpose X minus A transpose EI. That's my vector. So we have D components in RD. Okay, and so given A, choosing X to be the dark mean over all the point X star which exists of A transpose X, this ensures that V of X star A belongs to R minus D. Okay, so if I know A in advance, I can choose X star such that V of X star A is in RD. So by Blackwell theorem, this tells me that I can construct a strategy such that I don't know A in advance. I can construct a non-line strategy such that V of V of XT AT converge to the negative octant. And we know the speed of convergence is given by a Blackwell theorem. And the speed of convergence is square root of the L2 norm square of my vector. So here I don't have the square because I changed my mind while I was writing it. And so here, sorry, here I have a, what did I write? So here, sorry, I need some, well, actually it's correct. Let's put it like this. It's correct. It's weaker than what I wanted, but it's correct. And I just need to look at the L2 norm of my vector V, which is here, this one here. And obviously the L2 norm of this vector V is of the order of square root of D if A transpose X is at most 1. Okay, meaning that A and X, the two sets are in a dual from each other. So that's just an idea. Okay, just maybe there is here. Okay, here assuming I'm going to assume that just to normalize that for every, oops, I'm going to assume that A transpose X is smaller than 1 for every A and X. It's just normalizing. Otherwise, I would have another factor here, but it's irrelevant. So here, what is really important in this statement is that two things. There exists strategy such that the regret goes to 0. And this strategy is quite simple. You compute your average regret component-wise, you project on a negative octant, and you play strategic Blackwell strategy. So you solve the zero-sum game at each iteration. And the rates of convergence is 1 over square root of T, but this was expected, times square root of D. So that's a very powerful statement because it gives, I mean, approachability just gives the existence of regret minimizing strategy in one line of proof, as you can see. Well, actually, it's maybe a 3-line because it's a 3-line, but it's just because I'm on my tablet. So that's here. This could be the end of story, but it's not. Because why? Because here I have this. I'm going to add a remark. We know, or at least I know, that the optimal rate is not square root of D. It's not square root of D over T, but square root of log d over t. And this cannot be improved. So I'm going to skip the proof for the sake of time. So we know that the optimal rate is not square root of d, but square root of d equals t. So where is the issue? Here, the issue is that the L2, the distance from v up to r minus d is not the correct one. Why is it the case? Because we defined the regret. The regret was defined as the maximum over all of the components of an average of some average the average loss AT transpose XT minus the average loss of the vertex I. And we want to minimize this thing here. So here, if I'm taking this vector here, this was my vector v bar ti, you can see that the regret is exactly the L infinity norm of v bar ti, v bar t. But it's not exactly because it's the max between the 1 and 1, so the maximum between, or here I can put the max. It's not exactly true, but it's not exactly the maximum. Here, maybe I have the max component-wise of 0. And this is correct. So that's the regret. But Blackwell approachability, he controlled, what he controlled? He controlled not this thing here, but he controls the L2 norm. Same thing with the max. Component-wise, right? Those are component-wise. So you can see that there is an issue. Is the regret is defined with respect to the L infinity, and approachability is defined with respect to the L2 norm. So we are not in the geometry is not the correct one. So it will be impossible to get the correct rates of convergence by using the incorrect geometry. So here, maybe a solution, a tentative solution, is to change the geometry. So we want to change the geometry. So how can you do that? There is two ways of changing the geometry. The first one is to change the geometry of the ambient space. And the second one is to change the objectives and the reward. And this is the first thing we're going to do. And actually, that was Blackwell first connection. That's an idea of Blackwell. It was a connection between, that's how he connected regret and approachability. So we defined a new game. So Blackwell, the same one, defined an alternative game. An alternative vector game. Let's call it still v tilde. But if player 2 choose player 1 choose xt and player 2 choose at, still in the linear case, the vector is going to be the following one. It's not going to be at transpose xt minus the minimum and so on and so forth. It's going to be on the first coordinate is going to be at, and on the second coordinate is going to be at transpose xt. And this belongs to RD plus 1. And what is the target set? It's going to be C tilde, which is going to be all of the vector AZ such that Z is smaller than the minimum over all the X of A transpose X. And this has the correct geometry. Why? Because let's take a lemma. Very simple lemma that's going to say the following. RT is bigger than the distance from VT bar up to C tilde. That's a V tilde, right? but it's smaller than square root of 2 times the distance from VT up to CT. So here, the regret is perfectly controlled by the distance. While before, the regret here was not the right, you can see here, you didn't have the correct factor between the distance and the regret, and between the L2 and the L infinity norm, you have the square root of D factor, which is the one that arrives here. So at the beginning, if you're using the Euclidean geometry to control a quantity which is defined with respect to the L infinity norm, then you are off by a factor square root of D because of the difference between the L2 and L infinity norm. And at the end, you can see it in your rate. So here, I define a new target set such that I don't have this discrepancy, because the difference between the regret and the actual distance, the Euclidean distance from VT bar to this weird set here is exactly square root of 2, up to square root of 2, between 1 and square root of 2. So I'm in the right, this is the correct distance. And no, what does this say? This says that as a consequence, we know that the regret is, the expected regret is going to be smaller than, so maybe up to some constant, 1 over square root of T. And what I need to put on the top is no longer square root of D, but it's just the size of the vector, the norm of the vector. The norm of the vector is just the maximum over all A of the norm of A, L2 norm. And I also have this Z here, so maybe I'm just going to put the maximum over A and Z of A transpose Z. And this is a lemma, which is trivial. And I don't need to prove it because it's just a direct consequence of everything we did before. But here, this is very interesting, because if you instantiate this lemma, so let's make some example. If I'm taking A to be the Euclidean ball, so it's all the A such that A is smaller than 1. And I want A transpose, and what I'm going to take for X, the dual of this set. So for X, I'm also going to take the Euclidean ball. Then what does this, so that's and then I want to define the regret problem with respect to those things here. This result tells me that the regret, the expected regret, is smaller than, up to some constant, so just put my wiggle here, is smaller than 1 over square root of T. Okay, because the norm of A is smaller than 1, A transpose Z is smaller than 1, so here it's smaller than 1. So this is dimension independent. And it's one-line proof once you get everything. And this is something that it's not achievable. It's very hard to obtain such a result using standard machine learning regression techniques. It's very, very difficult to get this result here with standard machine learning techniques. While with approachability, it only took me like, as you can see, 0 line, because I didn't need to put the proof. So it's a very powerful technique, this approachability. So that's a very positive results. So I might have a very negative results. Okay. So the following is, that's positive. But a negative one is that it still does not answer the case, because if I take A to be -1 to the D, and X, I take the dual of this set here, X to be, so it's going to be the simplex over D, I get a regret that still scales as square root of D over T. So it's still, I still get this D here, which is suboptimal. So this change of geometry was interesting for two reasons, because I get the right, so here I have a 1. So I know that regret is exactly controlled by the Euclidean distance to a set. And sometimes it gives me very interesting results, such that here, in the case of Euclidean ball. But for this very specific case here, when A is L infinity ball, and actually the issue is, well, I'm going to skip this, but I have some issue with the geometry of this space. I still have a regret at scale as square root of D. So the dimension here is still paid in the full price, while I know that the correct speed of convergence should be square root of log D. So how can we get around this problem? The idea is, that's why my fourth section is what I call back to regret, but actually I don't really know why I call it like this. It's back to regret, and it's changing the space geometry. So I'm going to change the geometry of the ambient space. Instead of just changing the target space, I'm going to change the geometry of the ambient space. And my point is to get to be able to prove this result here. Theorem, there exist strategies in the finite case. So it's a finite case correspond to x is simplex over d, and a is minus 1, 1 to the d, such that the expected regret is smaller up to some constant. That's why I have this wiggle here of log d over t. And the proof is not that difficult, actually. It's not that long. So I'm going to do it because it's quite interesting. So the proof is the following. We're going to use what is called the exponential weight algorithm. And I'm going to say that xt plus 1 I is going to be proportional to the exponential of minus eta times the sum from s equal 1 up to t of at transpose ei. So what does it say? It says that I'm going to pick an action at random, obviously. We have to actually to have a random algorithm. And what is crucial is that the bigger this quantity here, the smaller the probability. So if an action I in the past behaved very poorly, meaning that the cumulative loss is big, then the probability of playing it in the future is going to be very small. So this algorithm just puts more and more weights to actions that behave nicely in the past. Okay, and the proof is just almost one line, and is based on the study of this potential. So we have the potential function. Here's, let's call it phi of z. So it's a function that goes to Rd in R, and defined by phi of z. So I should put a point here so that nobody is get upset. Phi of z is 1 over eta times log of the sum of exponential of minus eta zi. Okay, so I have this potential, right? This function here. And the proof now is based on the following Taylor expansion. I'm just going to do a Taylor expansion. Taylor expansion of phi. And here goes. So let's write, here I'm going to define at plus 1. Well, at, I don't know why I put plus 1 here, to be the cumulative sum of the small vector output by the nature. Okay, and I'm going to do the Taylor expansion of phi of at plus 1. Phi of at plus 1 Taylor expansion, so it's phi of at plus the gradient of at transpose at plus 1 plus at plus 1 transpose the Hessian of phi at some point, zeta, times at plus 1 over 2. And this zeta actually here, it's easy to see that zeta belongs to the the segments between 80 and 80 plus 1. And now if you make some computation, you can see that the gradient of phi is here. So if you compute the gradient of phi, you can see that component-wise it's minus eta times zi divided by the sum. So the gradient of phi is actually this guy here is exactly minus eta times xt plus 1. Now if you compute the gradient, the Hessian, sorry, you can see that the Hessian is dominated by eta square times the gradient over the diagonal. So this thing here, it's not difficult to show that this is smaller than 1/2 because I have these two here. Just make some computation. It's trivial actually, and I forgot eta square because I derived twice. Okay, so I have this induction now. So I have phi 80 plus 1 is equal to phi 80 plus something which is minus eta from xt plus 1 transpose 80 plus 1, so on and so forth. So at the end, I end up with so here I'm sorry, I don't have eta here because I divided by eta. I divided by eta here, so eta cancels out. It depends on how I define. Sometimes I put, sometimes I don't put it. So I'm in this, I'm over here. So I end up with the following. So I know that phi of 80 is going to be smaller than phi of 0. So I'm just going by my induction, minus the sum from t equals 1 up to t of xt plus xt transpose 80 plus eta t over 2. And the good thing is that phi of 0, this is just log d over eta, if you're just looking at the definition. And this thing here, phi of 80, you can see that this is smaller than minus the minimum over I of AT transpose EI. And this tells me that if I'm putting this guy here on the left, I have the following recursions. Tells me that T times RT is smaller. Well, it's an expectation because here I have XT, so it's everything is an expectation actually. So here it's the expected regret. T times RT is smaller than log D over eta plus eta T over 2. And so I just need to take eta to be square root of log D over T, so that this thing here is smaller than square root of log D over T. And that's it. That's the end of the proof. So here, I have a different algorithm, something that looks like completely different from Blackwell approachability. I just define a function, a probability here, xt, the exponential weight. I have this potential function, and I'm just making a Taylor expansion. Everything looks great. So you might wonder what is the connection? Oh, what is the connection? What are the connection with Blackwell approachability? And actually, it's just so I'm sorry about this. I'm trying to get the grip of my this tablet, and it's brand new. So here we might wonder what is the link with approachability. So let's good remark. So there is strong link with approachability, strong links with approachability. Why? It's because actually, if you look at the problem, we know that the objective defined by Blackwell, the first one I defined, actually is due to Hart and Mascolel. Oh, I should have put a name actually. Maybe I should put it somewhere. Can you still do it, or? I want to do it for sake of completeness. Well, I lost where I put all the name of all the people that works over here. Art also work a lot on this. Mascolel. Also Foster and Vora. Well, look at the survey. There is lots and lots of paper. So here it's a negative orthant. Blackwell say, well, I use the L2 norm to the negative orthant, which looks like this, right? So here's the L2 norm. That's the level set of the L2 norm. Okay, so that's Blackwell's strategy. Blackwell's strategy, what he did is when you're here, so that's VT bar, you compute the projection, and then that gives you a direction, and you're playing a zero-sum game with respect to that direction, and you end up on the other side of the upper plane. So that was Blackwell technique. Here, the exponential weight, we use this function phi, the potential phi of z, which was 1 over eta log the sum of exponential of minus eta zi. And this thing, if we're computing the level set of this function, it's no longer the same level set. The geometry is different, and it ends up something like this. Well, it's very difficult to make actually. So I'm trying to do something like this. So here it's there is some slope, and then it's closer to the. It looks almost like this. Okay, at the limit. So I'm going to use this. If I'm looking at the limit, so when eta goes to infinity, this level set are. So I like this picture, so I'm going to use it. This color. So that's the level set for eta. That's eta equals to plus infinity. And you see that it's just basically, instead of looking at the Euclidean geometry of the space, I'm using a non-Euclidean geometry defined by this function phi. And the algorithm is the same as Blackwell actually. So let's say I'm here. So here, if I have VT bar, what I'm going to do is I'm going to consider, I'm not going to project onto C and use this direction here as Blackwell did. I'm going to look at the gradient of phi. I'm going to take the gradient of phi of ZT. So it's basically this function here. So that's the gradient of phi of VT bar. And I'm going to play, actually what's playing exactly this is playing in the zero-sum game defined in that direction here, the direction of the gradient. And actually it's the same thing as Blackwell, because if you remember, if you just look at this picture, this direction here is exactly the same one at this direction here, which is the gradient of the L2 norm from VT bar to C. So here, basically what this algorithm is saying is use the same algorithm as Blackwell, except that instead of using the Euclidean geometry, use the geometry induced by phi, which is which has some slopes in at the infinity, and which is more adapted to the that looks like the L infinity geometry. The L infinity geometry is this one here in a rainbow, and the one induced by phi is the one in green that is closer to the one of the rainbow one than the red one. Here, because here, over here, you have a factor of square root of d. While between the green one and the rainbow one, there's only a factor of the square root of log. Basically, that's the idea. Okay, so that's the solution of the that's a solution of the regret minimization. So actually, we can be that's we need the following lemma. Sorry, I'm trying to write in French because I only have like 30 minutes left. So okay, actually, we have a stronger bond. A stronger bond holds. What do we have? We also have I'm going to write like this. RT is smaller than expectation. I'm not going to do the proof. It's smaller than log D over eta plus eta times the sum from t equals 1 up to p. I'm going to write it like this. You remember here, I used to write 80 plus 1, or maybe just 80 here. I used to write 80 plus 1, transpose the Hessian of phi taken at some point zeta, t, times 80 plus 1 over 2. I used to have this. And actually, what I can do is I can prove is that if I'm willing to lose this factor 2 here, I can replace, and you remember I said that zeta t was in the set 80 plus 1, was in the segment. And if I'm willing to get rid of these two, so I'm losing a factor 2 here, I can replace zeta t by at. So here it feels that the difference is very small, but actually it's not, because here this quantity here is still going to be log d over eta, which is smaller, plus eta times the sum from t equals 1 up to t. And since I have the Hessian of phi, if I'm computing the Hessian of phi, it's basically xt, so I will end up with this quantity here. So the sum from 1 up to d of xt plus 1 times I multiplied by at plus 1 square I. So here I'm not sure why I have plus 1s everywhere, but okay, maybe it's from 0. Maybe I should have, well, I'm just going to get rid of those plus 1. I don't, just a change of xti times ati. Okay, so I have these results. The proof is just actually it's also one line, and instead of doing the Taylor expansion of phi, what you're going to do is you're making a Taylor expansion of this guy here, and then you're making another Taylor expansion. So it's the proof is rather similar, but it's a bit different. So now you might wonder why is this interesting? Because we didn't gain much. Okay, if I'm taking the worst case, this doesn't give me anything more. Actually, it's even worse because I lost a factor 2. And this is where we're gonna win a lot, is when we're going to look at our fourth chapter, the bandit case. So what is the bandit case? The bandit case is the exact same setting, except the following. Except that only AT transpose E of IT is observed, and not the full vector. So you just get to observe your loss. An algorithm has only access to its loss and not the full vector. So in the thing I said before, it says that the feedback is of zero order, is just, you know, if in optimization, f of xt and not the gradient. That's the equivalent in optimization. That's if I was taking this in optimization. Okay, so here it means that I just get to observe the value function. So I'm querying a point. Here is the vertex, a pure action, IT. I'm querying a point, and I just get to observe the value of my loss. I don't get to observe the gradient. So there is two ways of solving this problem, no analysis. So there's two different ways. Two ways. The first one is the naive one. Is basically what you do is, with probability gamma, you play at random. And you estimate 80. This is doable. And with probability 1 is gamma, you play probably exponential weight. You play with the exponential weight using 80 hat. So that's the first technique. With some probability, small probability gamma, you say, well, I don't really care about the optimization problem. I'm just going to try to estimate. So with probability gamma, you just estimate the loss. And with probability 1 minus gamma, you don't care about what you're saying. You're just saying, well, I'm going to optimize my loss with respect to the sequence of estimate I got. And this is not difficult. Actually, it's trivial to show that with this technique, so that's technique 1, the regret is going to be of the order of gamma times t, because with each stage you're making, with some probability, you play at random, so you're losing a constant factor, plus 1 minus gamma that I'm going to discard, the error that the exponential weight is doing, so log d over eta plus eta times t divided by gamma. So this gamma here arises because when you estimate, you're trying to estimate AT, you have some variance, and the variance is 1 over gamma. So this is what you get if you're making a. So here I need to put some, and here I have some d also. That's just I don't want to do the proof of this result because it's optimal. And if you pick all the parameters that you want, you can show that this is smaller than dt squared over 1/3, I think. Something like this. Over, sorry. It's supposed to be d over t to the 1/3. Which is interesting because it goes to 0. Okay, so we're happy. But here, the point is we have 1/3. And that's because it's the naive one. Better solution.
Vianney, just what do you mean by estimating AT?
Well, because if you play gamma at random, so if you play at random here, actually I'm going to use it. So here the question is, how can you estimate AT? So you play, so you choose IT at random with probability xt of I. Okay, so I change my notation here, so I'm going to be consistent. So here 8xti. Okay, and this guy is going to be I. So we play AT equals I with probability xt of I. Okay, and now if you're saying, well, I'm going to define ATI, I'm going to estimate ATI by what I observe. So it's going to be ATI divided by the probability I had to play this guy, multiplied by the indicator that I actually play this thing. So here I'm going to estimate. So AT of I is a value which is, that thing is either 0 and 1. If IT is actually I actually choose is really I, then this equals to 1, and so I will have AT over I divided by the probability. And if IT is different from 1, this is 0. Okay, and you can see here that this is a good estimate because if I'm looking at everything, the expectation of AT of I, this is equal with, so with probability xti, this guy here is going to be 1, so it's ATI divided by xti, and with probability 1 minus xti, I play something else, and this is 0. And as you can see, this disappear, this is cancelled out. So the expectation of ATI is equal to ATI. So it's an unbiased estimator. So I can more or less compute ATI based on only my observation. And the thing is, if I'm looking at the variance of ATI, or actually just look at the expectation of ATI square, this is equals to, with probability xti, this is going to be ATI divided by xti square. And with probability 1 is xti, this is going to be 0. So here, well, 0 square, if I want to be precise. So it disappears. This guy disappears with this one. So here, the variance is ATI square divided by xti. That's why here you get a gamma. Oops, you get a gamma here. Actually, it's a gamma over d. That's why you get d here. Okay. So that was the naive solution. The better solution is to always use x3 follow the exponential weight algo, but directly applied. Sorry, I want to get some applied to the sequence ATI. Defined like this. And why this is interesting? And this here you have we have an important theorem due to Auerbach, Zabianchi, and Fisher that says that the expected regret is smaller than square root of log d times dt, d over t, sorry. Sometimes I'm mixing average and assumptions. And why is the case? And this is just because of this result here. So here in the factor t. And this result told us that the proof is one line actually, knows that we have everything. The proof, it says that, you know, we know that t times the expected regret is smaller than log d over eta plus eta times the sum from t equals 1 up to t, the sum from I equals 1 up to d of ATI square divided by XTI square times the indicator that IT equals I multiplied by XTI. Okay, that was this result here. XTI times ATI square. But here I replace ATI by ATI at, which was this definition. So here when I'm taking in expectation, so here I already put the expectation. So if I'm putting the expectation, I have expectation here, and I also have expectation here. And what happens is that here I have one of those XTI that disappear with the square. ATI, this guy is smaller than 1. But here I have the expectation of 1, of the indicator of IT equals 1. And the expectation of I indicator that IT equals 1, is exactly XTI. So here, this guy will also cancel with the second one. So I will end up with T times the expected regret is smaller than log D over eta plus eta times TD. Because all of those terms cancels out. And choosing, if you choose eta to be a square root of T over log D, T log D, no, the log should be numerator. This gives the results. And actually, T should be, sorry, lots of mistake here. Let's write it again. So eta should, the T should be like this. This gives the results. Okay. So basically, with exponential weight, you get in a bandit, you get square root of D over T log D regret. So that's the main result. Now I just need to speak about open problems. I don't know why I'm running out of time. So do you want to get my my open problems?
Yes.
Okay, so the open problems are actually a mixture of everything. The first one is basically is can we get square root of T bounds? Can we get square root of T bounds in bandit case with approachability? Why this is interesting? Because as I said before, the approachability is very strong results. Remember, when if I'm taking a Euclidean ball, I can prove with the approachability that my regret is it has a very precise statement. So that's the first one. Remember that I was able to prove that without bandit, in non-bandit, I was able to prove that the expected regret was smaller than the max over A plus the max of A transpose Z divided by square root of D. Another question is, what happens with bandit? I expect, for some reason, because, you know, when in bandit, I moved, in standard case, we move to square root of, we move from square root of log D over T we move to square root of d log d over t. So typically, when you move from first order to zeroth order optimization, you lose a factor square root of d. Typically, that's a typical thing. So here, I would expect that in bandits, we could prove that the actual correct rate should be something like square root of d over t times this maximum here. And if I was able to do this, if we were able to do this, it would be very impressive, because for the moment we in machine learning we only know how to solve two cases. We only solve the cases where x equals a and is equal to the L2 ball, and then the result we get is square root of d over t. And the other one is when x is the L infinity ball, and a is simplex, and we know that this gives something of the order of d over square root of t. So that's the only two cases we know how to solve, this one and that one. And you can check that in both cases, this intuition is is correct. Is exactly square root of d over t is exactly this thing, and d over square root of t is exactly that thing. So my guess is that this conjecture is true for some set A that are centered around 0 for the reason. But that's something that we'll be able to solve any case using a very unique and simple case, and you know, like only a trajectory strategy which is only based on the geometry of the problem. But to do that, we have another problem, which is the following. If I'm using, remember when I was using the expectation of RT, when we were trying to do I defined VT as AT transpose XT minus ATI at the beginning, and I want this to converge to negative orthant. This, I said that then the Blackwell strategy is called regret matching. That's the name of it. It's regret matching because you play proportionally to your regret. Matching regret. And the question I have is, if I'm using this case with in a bandit setting, is it possible to prove, maybe with a small trick, let's say, well, with some probability you sample at random, I don't know, is it possible to show that in this case, matching regret, this strategy has a regret that is smaller than d over square root of d over t multiplied by square root of d, the same one that's here? Is it possible to prove that we get such a result? And this is something which is actually maybe simpler than the first one, so it should be the first step to prove the first the conjecture one. So that's a very simple result that nobody knows how to prove, and apparently it should be true. So we have intuition that says that it should be true, but we don't know how to prove it. And finally, I'm just going to mention two other open problems if you're interested. The third one is in a stochastic case. So if I'm assuming that AT are IID according to some distribution mu that I don't know, what can we say about the error, the distance from VT bar up to C? Let me say something more, because in bandit, in a stochastic case, so if I'm looking at stochastic bandit, the regret, we can prove that the regret scale as log t and no longer square root of t, which is of course way smaller than square root of t. And so my question is, that's for regret. My question is for approachability. Can we have something similar in the stochastic case? And the fourth one is something completely different. It's in partial monitoring. So here, if my feedback, Okay, so the question is, so so you pick, so you know that your reward is AT transpose XT, but the feedback is AT transpose H times XT, where H is okay, let's say D-empty matrix with value in R or P. Okay, and the question is, what can you say about the regret? Can you prove that the regret typically is smaller than something like T to the -1/3? That's the first question. But that's some stuff I haven't mentioned in the talk. So for you, I'm leaving it open over here. Those two open questions here, the first one and the second one. Basically, the question is, can we do regret minimization in bandit feedback with approachability strategy? The reason is that since approachability is the geometry is adapted to the problem, we should be able to improve lots of existing results and go in a direction, totally opposite direction to what is done in machine learning. So it could be very interesting and very impactful. But I have no idea how to make it. And I am way over time, but yeah, I really don't care actually. So I'm not really sorry. And those two open problems are very, very interesting again. And if you are even slightly interested, feel free to contact me. That's it.
Okay. So thank you very much. Are there more questions?
I have a question.
Yes.
Do you hear me? You used the term potential when you were working with the weighted exponentials.
Yeah.
So in what sense is it a potential? It's related to potential games, or is it related?
Oh, actually, it's more like it's more like a Lyapunov function. It's a quantity that decreases with time.
Okay, and so in this, it is like a Lyapunov function.
Yeah.
But why is it called potential? Because it.
Why is it called potential? Actually, it has nothing to do with potential game. Nothing at all. I think it's yeah, I don't know. Yeah. So I have to be honest. It's a question I've never asked myself. Maybe someone else has some idea about this. Maybe Sylvain or Marc. I don't know, because it's.
It was like a distance, and it was decreasing along the trajectory.
Yeah, so that's
yeah. It. Oh, by the way, maybe you should have also mentioned Benaim and of power.
Ah, yes, you're right. Here you also have like, oh, well, they're going to be in red. So I forget them at the beginning, but here, Benaim and of power.
Can you use other functions on this particular function?
Sure.
Yes, actually, you can use. So if you go back to my here, you can use any function.
Yeah.
But that basically the gradient is the gradient has positive value. No, it has positive components, non-negative components. Any function with gradient has non-negative components works, and you do the exact same technique. But the proof, actually, the proof here, if you're looking at the proof, I'm only instantiating the value of phi over here. When I go from this line to that line. Here, if you're taking any other function, basically you will still get phi of AT. So then you need to control how phi is going to be far away from your minimum. You need to control phi of 0 as the two direction. This thing here is always the same because you played according to this guy here. And basically here you still get eta t over 2. And you can use any other function. Actually, it's like instead of doing Euclidean descent, you're doing mirror descent. It's basically the same thing. You're switching your geometry of your space. And by the way, for this, I know there is an upcoming intense exhaustive survey by Sylvain that is arriving soon. So you should well, just wait for it. But also those connections between different geometry.
Excuse me. What can be said here when you added stochastic? You transformed it to a controlled IID process because you took the AT as IID. Now, what happened if you try to move to the complete stochastic game case, where you have transition probabilities and so on?
So in the stochastic game, it's much more difficult because the expectation has to be understood as because you will almost never. I mean, depending on the class of stochastic game you take, but if looking, for instance, at absorbing game, you will never have almost short convergence. Or otherwise, the condition, the requirements are going to be very strong. So there are two lines of works actually for stochastic game. The first one is, well, I want to have almost short convergence to my target set C, and this implies very, very strong requirements on your functions. So that was a paper by I forgot his name, so it was I forgot. So I'm sorry about for him, but I forgot. And the other type of technique is if you're looking at absorbing game, and then there is, if you put more structure, so not just absorbing game, but quitting game. So it means that, well, let's say actually it has been generalized for absorbing games. So if you just consider absorbing games, then you can derive condition for approachability, but not almost short approachability, just approachability in expectation, and actually something called weak approachability, which might be you might know more about this afternoon. I don't know if Mark is going to speak about weak approachability or not, but basically instead of looking at the convergence it's like instead of looking at the uniform value, you're looking at the convergence of the value for the T stages game. Mm-hmm. So yeah, so for the moment, it's on stochastic game are only considered for quitting games, absorbing game, or otherwise general stochastic game, but with very strong requirement.
Okay.
So I have a question regarding the formulation of the Blackwell theorem you presented.
Yeah.
There is another one that says that the target set C is approachable if and only if all the half spaces that contains it are also approachable.
Yes.
Is there a fundamental difference between the two? Because the proof leads to the same result, except
no, exactly the same. Actually, it's exactly the same theorem, the same statement. And so yeah, actually, if you're looking at the proof, basically where it says it's one is a consequence of the other. Okay. So here, if you're using this here, there is term here for every y there is h. This implies that every half space that contains C is approachable. And like this is what I did here. Yeah. And if you're using the fact that every half space is approachable, then you can define the strategy. So it's exactly the same thing. Okay, it's just basically it depends on which order you present the different arguments, but it's the same thing.
Okay.
Yeah. Yeah.
Okay, so